Good morning. I'm Doug Ming from NASA's Johnson Space Center, and it's my honor to introduce our next two speakers. First of all, I want you all to put on your seatbelts, get ready to blast off from planet Earth. We are now heading out into the solar system, and our destination is Mars. I was thinking about the 100th anniversary of MSA, and 100 years ago, Mars was a really heated debate among scientists. It wasn't about the minerals. It was about if there were canals on Mars that had been developed by some extraterrestrial beings. Percival Lowe first presented that hypothesis, but as telescopes got a little bit better resolution, his hypothesis was met with a lot of skepticism. In fact, that debate raged for quite a few years, and then finally in the 1960s, NASA sent a flotilla of spacecraft since that time to Mars, and we now know that Percival Lowe's hypothesis was not correct. We did not see these extraterrestrial channels. But this flotilla of spacecraft that got to Mars has given us an incredible amount of information about Mars, and we'll talk about that this morning. Before I go on, this flotilla that I was talking about, we have Dr. Jim Green. Jim in the front row. Jim is NASA's chief scientist and was the director for the Planetary Science Division at NASA headquarters. He led the science missions here at NASA, these robotic missions to Mars and beyond, as well as the research. So it's great to see Jim here. First of all, I'm going to introduce the two speakers. The first talk, and what you're going to see here is a very dynamic difference between the two, the information you'll hear this morning between the two speakers. The first talk is about the surface mineralogy and geochemistry and what we have determined by these landers and rovers that have got to the surface. And particularly this morning, we're going to hear about the mineralogy from an X-ray diffraction unit, and it's so fitting that the first X-ray diffraction unit on Mars happened 100 years after Lau first used X-ray diffraction. So it's pretty cool that we're able to expand that from planet Earth and take that to Mars. So we'll hear Liz Rampe talk about the mineralogy that has been determined by this chemin instrument in Gale crater. Then we're going to look at a very different part of Mars. And Dr. Hat McSween from the University of Tennessee will talk about these meteorites that we have in hand here on Earth and how they are different from the things that we see on the surface. So with that, I'm going to turn it over to our first speaker, Liz Rampe, to give her talk, which will be on looking at Mars's ancient mineralogy and doing that through the eyes of X-ray diffraction.
Hi, everybody. I am honored to be here. Thanks so much for inviting me. It's a pleasure to be here, and I'm so excited to talk to you about the minerals that we've been finding with the chemin X-ray diffractometer, which is an instrument on the Mars Science Laboratory Curiosity rover in Gale crater. I'm going to focus on the mineralogy of ancient fluvial lacustrine deposits that we've been studying. These deposits are about 3.5 billion years old. And I'll talk about the igneous sources for these deposits and their aqueous history. So Curiosity landed in Gale crater in August 2012, so we've been up there almost 7 years now, which is hard to believe. Time flies when you're having fun. Gale crater is an impact basin. It's about 150 kilometers in diameter. And what's special about Gale crater is there's this 5-kilometer tall mound of layered sedimentary rock in the middle that we call Mount Sharp. And we know that based on a visible near-infrared reflectance spectroscopy from orbit that some of these lowermost layers show variation in the mineralogy that suggests they preserve some environmental changes that happened on Mars about 3.5 billion years ago. So if we zoom into these lowermost layers, this is a high-rise image of some of those layers. So just to orient you, we're looking straight down at some of those layers, and the peak of Mount Sharp is down and to the right. But some of these layers have specific mineral signatures. This ridge, which we call Vera Rubin Ridge, has a signature of hematite, and I'll talk much more about Vera Rubin Ridge today. And then some of these layers have mineral signatures of clay minerals and sulfates. And this mineralogical stratigraphy, where we see phyllosilicates underlying sulfate units, is recognized globally across Mars. And the hypothesis is that these layers are preserving a dramatic climate change that happened on Mars about 3.5 billion years ago, where the Martian surface went from relatively warm and wet, where phyllosilicates were precipitating, to a drier climate where we were precipitating sulfates. And so with Curiosity, the goal is to drive up these lowermost layers of Mount Sharp, study the sedimentology and the composition of these layers to determine what these ancient climates were like on Mars 3.5 billion years ago, and whether they would have been habitable to ancient microbial life. So Curiosity, we just ended an extensive campaign on Vera Rubin Ridge. We're currently in this clay unit in green. I'm going to show you the mineralogical results up through Vera Rubin Ridge today. So this is the Curiosity's traverse over the last almost 7 years, and we've gone almost 21 kilometers from our landing site out on the plains and then across the plains and around this large aeolian dune field, and then our turn to the south and our drive up those lowermost layers of Mount Sharp. And I'm going to show you a few of the outcrops that we've encountered so you get an idea of the depositional environments here in Gale Crater. I'll show you an outcrop very close to our landing site, another outcrop near a place that we called Yellowknife Bay, another place at a stop called the Kimberley on the Plains, and finally an important outcrop at a place called the Pahrump Hills. So this is an outcrop that we saw very close to our landing site. It was revealed by Curiosity's descent rockets, which blew away a lot of the surface dust and sediment. This conglomerate has clasts that are up to about 1 centimeter in diameter, and they're well-rounded, suggesting deposition in a fluvial environment. The Yellowknife Bay outcrop is made up of fractured mudstone, suggesting deposition in a lacustrine environment. And these fractures are enriched in magnesium, suggesting that there were magnesium-rich fluids moving through these sediments before they lithified. At the Kimberley stop, we see these beautiful sandstone beds that are just gently dipping towards the center of the crater. And these are consistent with prograding deltaic deposits. And then this is an outcrop that we call the Pahrump Hills. It's a really important outcrop for Curiosity because it marks the beginning of our investigation of those lowermost layers of Mount Sharp and what we call the Murray Formation. For scale, this is about 12 meters of vertical stratigraphy, and this is our traverse, which was about 100 meters. And Pahrump Hills and much of the Murray Formation is made up of laminated mudstone. You can see these millimeter scale laminations in the background of one of our images of one of the drill holes here. And this suggests deposition, again, in a lacustrine environment. Okay, so now that you've seen some of the outcrops, we can come up with a depositional model to explain them. So if we were on Gale Crater, in Gale Crater, 3.5 billion years ago, we would have seen rivers and streams emanating from the crater rim, depositing those conglomerates that we saw in the plains. These rivers and streams would have been flowing into probably a series of lakes on the crater floor. And where these streams entered the lakes, we've gotten those prograding delta deposits. And of course, in those lakes, we were depositing those laminated mudstones. This red line represents Curiosity's traverse, where we started primarily in fluvial deltaic deposits, but have really been studying lake and lake margin deposits for much of the mission. And Curiosity has a variety of science instruments to study these rocks and the modern environment. I'll point out just a few of them that I'll mention today. So on our arm, we have our sample handling system, including the drills, scoop, and sieves, and this is how we get sample into chemin. Also on the arm, we have the alpha particle X-ray spectrometer. It uses particle-induced X-ray emission spectroscopy, or PIXI, and XRF to get bulk chemistry of our targets. On the inside of the rover, we have 2 laboratories. SAM is a gas chromatograph mass spectrometer, and we can use it to help us constrain the mineralogy, but also identify organic compounds. And then, of course, we have chemin. Chemin is a combination XRF-XRD. We can only get qualitative geochemistry with XRF, but we can get quantitative mineralogy down to a detection limit of about 1 weight% with our XRD. And I hope this movie will work. It's just a little movie to show you how chemin works. Please, 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 is it working? It's such a good movie. Okay, it's not working. Well, I will tell you how chemin works. So we take a drilled rock powder that's drilled from a few centimeters below the surface, or a scooped sample. We deliver it to one of 27 reusable sample cells. We work in transmission mode, so we're transmitting X-rays, an X-ray beam through the sample. We apply piezoelectric pulses to those cells so that we get convective grain motion in the cells, and so we get all different orientations exposed to the beam. We have a CCD that collects those two-dimensional X-ray diffraction patterns. We sum those rings circumferentially to get the traditional 1D diffraction patterns, and we do Rietveld refinements on those 1D patterns to get quantitative mineralogy and the unit cell parameters for the major phases. And this on the left is our first chemin two-dimensional X-ray diffraction pattern from a sample that we called rocknest. It's from an Aeolian sand, and then this is its 1D X-ray diffraction pattern. And just like Doug said earlier, since we're reflecting on the last 100 years, it's really fitting that we collected this pattern exactly 100 years after the discovery of X-ray diffraction by crystals. Okay, so now you've seen the rocks, you know how the instrument works, let's talk about the mineralogy. This again is our traverse. These dots represent places where we sampled along the traverse. Black dots are modern Aeolian samples like rocknest. Gray dots are ancient Aeolian sandstones. And then the yellow dots are those ancient fluvial lacustrine deposits that I'm going to focus on today. This is the stratigraphic column for all of the rocks that we've studied through Vera-Rubin Ridge. It's about 350 meters of vertical stratigraphy. These black dots represent places where we've drilled and analyzed samples with chemin. You'll notice a lack of those drill samples over about 150 meters of section. We had an anomaly with our drill. But the engineers figured out a workaround for it, which thank goodness for the engineers, because chemin is incredibly reliant on that drill for receiving samples. Okay, these bar charts show you the mineral and X-ray amorphous abundances for all of those fluvial lacustrine samples that we've drilled to date. I know this is overwhelming, but every color represents a different mineral. And I'm going to break them down by mineral group, but what I want you to just appreciate is the variety of the mineralogy and how it changes within the stratigraphy. So let's start breaking that down by mineral group, and I'm going to start with igneous silicates. So in this dark gray color is plagioclase, in the medium gray is potassium feldspar, light gray is pyroxene, green is olivine, this medium blue is cristobalite, this bright blue is tridymite, and these light blue, which we don't see much of, is quartz. Plagioclase is the most abundant igneous silicate in almost every sample, and I've labeled the highest abundances for each of these minerals just so you get a sense of how much is in here. But it's also the most abundant mineral period in almost every sample. Shauna Morrison, who's going to give the talk in the next colloquium, led a pair of papers that came out in American Mineralogist last year that demonstrated that we can use the refined unit cell parameters to constrain the crystal chemistry of the major phases. And based on the unit cell parameters of the plagioclase, that composition is generally consistent with andesine. The only sample that did not have abundant plagioclase is the sample called Winjana. It was drilled from the Kimberley, so from those deltaic deposits. It has abundant potassium feldspar, whose unit cell parameters are consistent with sanidine. It also has the most abundant pyroxene of any of these fluvial lacustrine samples. And if we look at those mafic silicates, the pyroxene and the olivine, we notice that those abundances decrease going up section. Unfortunately, because of the low angular resolution of our instrument, we cannot confidently constrain the type of pyroxene present in our samples. Another interesting thing to point out is two of these samples from the Pahrump Hills member had abundant crystalline silica phases. So one of these samples had abundant cristobalite, one had cristobalite and abundant tridymite. Of course, these are low pressure, high temperature silica polymorphs. And tridymite especially was quite a surprise to the chemin team because Mars is generally a basaltic planet. On Earth, we usually find tridymite in rhyolite, so more evolved rocks. And so it's still puzzling as to why this sedimentary rock here has such a high amount of tridymite. And I've labeled these as igneous silicates, but some members of the chemin team are looking into the possibility of the cyanidine and the tridymite being hydrothermal phases. Okay, moving on to the iron oxides. Magnetite is in black, hematite is in red, and then oxygonite, which is an iron oxyhydroxide that is also chloride bearing, is in brown. And you notice that magnetite is prevalent at the base of the section, but hematite becomes especially abundant going up section. So this is telling us something about the redox conditions. We found trace amounts of oxygonite at the base of the section, and then didn't see it again until we got to the top of the Vera-Rubin Ridge, where it was quite abundant in one of these samples. And oxygonite is an important indicator mineral because crystalline oxygonite, like we find with chemin, forms in acidic and saline fluids. We also see evidence for variation in the hematite crystallite size within the section. This is a mosaic of the top of the Vera-Rubin Ridge, and what I just want you to notice is that there are a variety of colors. Some of these rocks are red, some of them are beige, some of them are gray. And we drilled 2 of these red outcrops. This is the Stower sample drill hole, and for scale, these drill holes are only about 1.5 centimeters in diameter. This sample had the most abundant hematite of any sample we've drilled to date, with about 16% weight hematite. We also drilled one of those gray outcrops, and this is the Highfield drill hole. This sample also had abundant hematite. Again, that was a surprise to the team because of the gray color, but of course this just means there's gray hematite present, and gray hematite is more coarsely crystalline than red hematite, where crystallites with a size above over 5 microns, I think, appears gray. But what's important also about gray hematite is that it commonly forms from the recrystallization of nanophase iron oxides like ferrihydrite in hydrothermal fluids. So this could be a hydrothermal indicator here. Okay, moving on to the sulfates. The most common sulfates that we find are calcium sulfates, and they're especially prevalent up section. Yellow is anhydrite, this light yellow is basanite, and this olive green is gypsum. And we see sometimes all varieties of the calcium sulfate in the same sample. And we also see them in veins usually. Jarosite is in this pink color, and we see it throughout the Murray Formation, but it's most common in this Pahrump Hills member. And jarosite is another important indicator mineral for us. Again, it's a ferric sulfate that forms from acid sulfate fluids in a pH of about 2 to 4. Another important finding about this jarosite in one of the samples from the Pahrump Hills is that the SAM instrument did potassium-argon age dating on it and got an age date of 2.1 billion years. This is an amazing discovery because remember, these sediments were deposited by lakes 3.5 billion years ago. And so this relatively young age for jarosite suggests that there was liquid water present on or in the subsurface of Gale crater for over the course of maybe 1.5 billion years. Maybe it was just intermittent, but that's very important for our understanding of the habitability of the Martian surface and near subsurface. Okay, and so the fact that jarosite is so young and the fact that we see calcium sulfate in veins suggests that sulfates are late diagenetic products in Gale crater. Okay, the last mineral group I'll talk about are the phyllosilicates. We see them in almost every fluvial lacustrine sample, up to about 25 weight percent, but down to 0 weight percent in a few of these samples from the Pahrump Hills. We can use the 001 and 02L peaks to help us identify the type of phyllosilicates present. And in most of these samples, the phyllosilicates have a basal spacing of about 10 angstroms, which is consistent with a collapsed smectite. But we do see some variability within the section, and the first thing I'll talk about is there is one expanded smectite at the base of the section in Yellowknife Bay. So these are the chemin XRD patterns of those 001 peaks for the John Klein sample in yellow and the Cumberland sample in gray. These were both drilled from the base of the section just a few meters apart laterally, but the phyllosilicate in John Klein has a 10 angstrom basal spacing, but the phyllosilicate in Cumberland has a 13.5 angstrom basal spacing. So remember, Yellowknife Bay had that evidence for magnesium-rich fluids moving through here. So our hypothesis is that those magnesium-rich fluids partially chloratized the smectite here, so precipitated some magnesium hydroxide in the interlayer site to keep that structure propped open. So again, I said most of these phyllosilicates have a 10 angstrom basal spacing, and this is an example of Duluth from the top of the section and Sabina near the middle of the section. This peak is actually a Kapton peak, which lines some of our cells, so it's not a phyllosilicate. But then some of these samples have phyllosilicate with a 9.6 angstrom basal spacing. So this is an example from the Udom sample in red, which is just above the Pahrump Hills, and in black is a sample from Rock Hall, which is from the top of the section. We think that this 9.6 angstrom peak is from ferriporphyllite. Ferriporphyllite is a ferric phyllosilicate in the porphyllite talc group that commonly forms from hydrothermal alteration. And we think that this is a hydrothermal alteration product because these samples also commonly contain gray hematite and opal CT, which can form under hydrothermal conditions. Okay, we also see variations in the O2L peak within the stratigraphy, and this is a measure of the B-axis of the crystal, and it's telling us about the dioctahedral versus trioctahedral character of the phyllosilicate, where trioctahedral phyllosilicates like saponite have an O2L peak with a slightly higher D spacing than that of dioctahedral phyllosilicates like montmorillonite. So here I'm just plotting the O2L peaks from phyllosilicates from different parts of the section. Cumberland in blue is from the base of the section. Marimba in green is from the middle of the section, and then Duluth in black is from the top of the section. And you can see that the O2L peak for Cumberland is furthest to the left, so has the highest D spacing, and it's most consistent with a saponite. And then moving up section, that O2L peak moves to the right, suggesting that we are moving from trioctahedral phyllosilicates to dioctahedral phyllosilicates going up section. And dioctahedral phyllosilicates form in more intense weathering environments in open systems. So our hypothesis is that the style of weathering and that intensity of alteration is changing going up section and going through time. And actually this is consistent with the decrease in the abundance of mafic silicates going up section. Those might have just been weathered out going up through time. Okay, I'm pretty sure I don't have a lot of time to talk about the X-ray amorphous materials, but I just want to mention them. It was a complete surprise that every sample that we have analyzed to date, not just these ancient fluvial lacustrine samples, but also the ancient aeolian samples and the modern aeolian samples, have abundant X-ray amorphous materials, 20 to 60 weight% of every sample. We can constrain the composition of this X-ray amorphous component using the crystal chemistry from chemin and the bulk chemistry from APXS. And based on that, it's not consistent with a basaltic glass or an impact glass. So we don't completely understand how they formed, how they got there, and I don't think we will until we can return samples to Earth and study them using TEM and synchrotron techniques. Okay, just to conclude, we have learned a lot about the depositional and alteration history of Gale Crater just based on chemin mineralogy. We see that these ancient fluvial lacustrine rocks, primarily there were basaltic sediments deposited in these environments with possibly some input from more evolved sources. The smectite, we think, formed shortly after deposition, but then diagenesis produced iron oxides and sulfates and might have altered the smectite in some locations. The identification of magnetite versus hematite within the section indicates that some of these diagenetic fluids had variations in redox conditions. The gray hematite and ferriporphyllite suggest that some of these diagenetic fluids were warm. The presence of jarosite and octagonite indicates that some of these diagenetic fluids were acidic and saline. And the fact that jarosite is so young and that we see calcium sulfate primarily in veins suggests that sulfates were very late diagenetic products. So chemin has helped us identify a diversity of habitable aqueous environments in Gale Crater that spanned over 1 billion years. And if we're looking forward to the future of Mars surface mineralogy, it's all about Mars sample return. So the next NASA rover to go up will go up next year in 2020. It will have the ability to cache about a dozen samples, and so we hope that we will return those samples to Earth in the next decade or two so that we can study them with our fantastic instruments that we have here on Earth, constrain the crystal chemistry, constrain the composition of those phyllosilicates, and really figure out how in the world those X-ray amorphous materials got there. Thanks.